So this video is part 3 on the conservation of energy. You should have just finished the video on what the definition of mechanical energy is and how conservation of energy applies. And so what we're going to do is look at some situations where we can apply the conservation of energy. Conservation of energy, again, let's just back up here, says that if the mechanical energy is conserved, then the delta KE plus the delta PE are 0, or another way, this is probably a useful way, is that the total energy before has to equal the total energy afterward. And also, as you may remember, if you back up to conservation part 2, that the total amount of work done to start the system is how much mechanical energy there is. So let's consider this kind of roller coaster. These are by far the most common kind of roller coasters, called gravity roller coasters. So what they're doing here is they are doing work on the train to get it up to the top, get the cars and the roller coaster up at the top of the first hill. And at the top of the first hill, then the work is done by this motor that's down underneath by drawing it up by a chain. And all of the energy is in the form of potential energy at the top. And then it slowly works its way over the top. And as it zips down this first hill turns most of that potential energy into kinetic energy. And then after that, it's just a matter of constant conversion. Down here where you would see it has a lot of kinetic energy. And then as it loops this loop, it's called a clothoid loop. At the top, it would have more potential energy, but it still has some kinetic energy to make it around. It makes some other kinds of loops up and down. But notice that it is true that none of the hills on the roller coaster is as tall as the first one, and it never will be. The first hill has to be the tallest hill on a gravity-type roller coaster. Now, we can also break apart here for a second and discuss there are other kinds of coasters called induction coasters at Six Flags. What's it called? Mr. Freeze is an induction coaster, and it doesn't follow these rules because it works on a different set of principles. But a gravity coaster, one that looks like this, where it takes you up a big hill to start off with, this is all done by changes of kinetic energy to potential energy and back and forth. So potential at the top, primarily kinetic, going on around. And you may even notice on some of these rides that they actually take out some kinetic energy in certain places. Here's another one. Same thing's true. You start out here, you go up this first hill. The perspective here is probably a little messed up because it looks like you're going pretty flat across the top of this, but I would say it most likely actually is working its way downward as you go forward. But all of the energy is put in here in this first hill, and after that it's all potential energy and then kinetic energy as it moves around through this. So here's just a drawing of the real simple coaster. So this must be the first hill. It has to be the highest. So the potential energy is the maximum. It works its way down. Kinetic energy increases. It's still increasing, but if we change some back into potential, then more. So the potential energy highest at the top of the first hill, kinetic energy the highest at the bottom point. And if I'm looking at this from my perspective, I'd say this is the lowest point. But then it has enough kinetic energy to make its way back up this hill as long as this hill is lower, and just keeps exchanging kinetic and potential energy until it finds itself back at the starting place. This would actually be this part where you load on, and then you get hauled up to the top of this first hill. All right, so that's a gravity-type roller coaster, and we're going to spend one more video looking at a gravity-type roller coaster, and then we're going to be done with this.